All right, get ready because we're doing a deep dive today into some physics class notes. But these aren't just any old notes.
Yeah.
First of all, they're dated October 7th, 9th, and 11th, 2024. So they're basically brand new, fresh out of the lecture hall.
Practically.
And you know how handwritten notes always have those little diagrams and like side comments that make things click? I'm really hoping we can uncover some of those aha moments together.
You're absolutely right. Those little personal touches, they really can help make all the difference. And what's really exciting is just thinking about how physics just connects to everything around us, whether it's like the latest tech or even just explaining why the sky is blue. It all comes back to those fundamental principles.
Okay, so first page.
Mm-hmm.
And right at the top, it says 10,000 atoms to be the size of a virus. Whoa.
Mm.
That's like a serious reality check right there.
Right.
It's easy to forget how tiny the building blocks of like literally everything are.
It really puts things into perspective when you think about it like that. And speaking of tiny things behaving in unexpected ways, the next note here, it mentions ferromagnetism and MRI machines. I mean, you wouldn't think those two have anything to do with each other, would you?
Not at first glance, no.
Ah.
So what's the connection?
Well, ferromagnetism is the kind of magnetism we see every day, like with fridge magnets. It's all about how the electrons are spinning inside a material. Now, if you amplify that effect to like a much stronger level, you've got the powerful magnets used in those MRI machines. They create this magnetic field that interacts with the atoms in your body, and this lets doctors see these incredibly detailed images of your insides.
So something as basic as a fridge magnet is like a stepping stone to understanding this complex medical technology. That's physics for you, always full of surprises.
Hmm.
Okay, the next section is titled Forces on Charged Particles. And there's an equation here. F equals QVB Beeson.
Ah, yeah, this is a classic. It describes how charged particles experience a force when they're moving through a magnetic field. That equation basically breaks down all the factors involved.
Okay, there are a ton of diagrams here. Arrows pointing every which way. What's the deal with all the directions?
That's the thing about this force. The direction is super important. It's always at a right angle to both the particle's velocity and the magnetic field. So, like, picture this. If the particle's moving north and the magnetic field's pointing east, the force will act either straight up or straight down.
So no matter what, the force is always perpendicular to both the direction of motion and the magnetic field. That's kind of hard to visualize.
Mhm.
Maybe that's why there are so many diagrams.
Yeah, visualizing 3D can be a bit tricky. And the sign of the angle in that equation that helps us figure out exactly how strong the force is. When the angle is 90 degrees, the force is at its maximum. But if the angle is 0, there's no force at all. It all comes down to the relationship between the particle's movement and that magnetic field.
Yeah, starting to make sense. But why should we care about the force on one single tiny particle? Does this actually like affect our lives in any way?
More than you might think. This principle is how electric motors work. The interaction of magnetic fields and moving charges creates rotation, which powers everything from your car to your electric toothbrush.
So that tiny equation explains why I can get to work and have clean teeth. Now that's what I call applicable knowledge. Okay, there's a note here that says, what if charge is held? What is the direction of force? And there's a diagram of a stationary charge just sitting in a magnetic field.
This is a good point to highlight. If the charge isn't moving, there's no magnetic force acting on it. Movement is essential for this force to come into play.
Interesting. So it's not just about being in a magnetic field. The charge has to be like actively moving through it to experience a force.
Yeah.
Okay, next up, work and energy in magnetic fields. Sounds kind of intimidating.
Don't worry, it's actually a pretty elegant concept.
Yeah.
There's a note here that says, if B is uniform and in the same direction of space that the particle travels, then the magnetic field does not affect the speed of the particle.
Okay, before we go any further, can you remind me what work means in physics? Sometimes those basic terms slip my mind.
Sure, no problem. Work is done when a force causes an object to move over a distance. But here's the thing. The magnetic force always being perpendicular to the motion of a charged particle. It can't actually do any work on it. It's like if you imagine pushing a swing sideways, you're applying a force, but you're not making the swing go any higher or lower, just changing its direction.
So the magnetic force is just kind of steering the particle, not speeding it up or slowing it down.
Precisely. And because no work is being done, the particle's kinetic energy, the energy of its motion, stays constant.
Uh-huh. So even though it's experiencing a force, its energy isn't being drained away. Okay, flipping the page. And we've got a diagram that looks like some kind of crazy roller coaster. What is going on here?
That's a mass spectrometer, a device that separates particles based on their mass to charge ratio. So imagine you have a bunch of different particles all mixed up. The mass spectrometer uses magnetic fields to sort them out. like a high-tech sieve.
Okay, I'm intrigued. How does it actually work?
First, the particles are given an electric charge. Then they're accelerated through an electric field. This gives them a specific velocity. As they enter a magnetic field, that force we talked about earlier kicks in, bending their path into a curve.
Okay, I see. There's a note here that says, no, VBR, measure M. What does that mean?
That's the key. By controlling the magnetic field strength and the particle's velocity and then measuring the radius of that curve, we can calculate the particle's mass.
So by carefully measuring the path of this particle, we can essentially weigh it.
Exactly.
That's how we've been able to identify unknown substances and isotopes in fields like chemistry and biology.
Even forensics.
Wow, that's way cooler than I expected. Who knew those curved paths held so much information? All right, what's next in these notes?
Now we're getting into the flow of charge, or what we call current. It's kind of like water flowing through a pipe, but instead of water molecules, it's electric charges on the move. And the notes have this equation. I equals delta Q over delta T. This helps define current.
Right, it's all about how much charge passes a point over a certain amount of time. But then there's this note that says, moving charges create magnetic fields. Is that where electricity and magnetism start to become best friends?
Exactly. That's one of the most fundamental concepts in electromagnetism. Moving charges like those in an electric current create magnetic fields around them.
To calculate the force on a wire carrying current in a magnetic field, we've got this equation, F equals ILB.
Right. That equation helps us understand how much force that wire experiences based on the current, the magnetic field strength, and the angle between the wire and the field. Just like with a single particle, the direction of this force is always perpendicular to both the current direction and the magnetic field.
Hold on a second. Doesn't this tie back to how electric motors work?
You got it. This force on a current-carrying wire is what makes motors spin. We strategically arrange wires and magnets, and bam, we get controlled rotational motion.
So we're seeing those same basic principles play out both at the tiny particle level and the bigger machines that are all around us. It's amazing how connected it all is.
Okay.
Turning the page. And we've got magnetic flux and Faraday's law, which sounds pretty intense.
It's all about how magnetic fields can actually create electric currents. First, we got to understand magnetic flux, which basically tells us how much magnetic field is passing through a particular surface. Think of it like counting how many magnetic field lines are poking through a specific area. We calculate it using the equation phi equals MBA cos, taking into account the strength of the magnetic field, the area, and the angle involved.
Okay, there's a diagram here of a coil of wire inside a magnetic field. Is that what's being described?
Exactly. Now imagine that magnetic flux changing either by moving the magnet, changing the coil shape, or rotating it.
Okay, I'm on the edge of my seat. What happens then?
Well, that's where Faraday's law comes in. It basically tells us that a changing magnetic flux creates what we call an electromotive force, or EMF, which can drive a current in a circuit. You can think of it as a sort of electric pressure that pushes those charges along. We can describe this using the equation I equals delta phi over delta T.
Whoa, so playing around with magnets and wires can actually generate electricity. That seems like magic.
It might seem like magic, but it's pure physics.
Yeah.
This is the principle behind generators, which convert mechanical energy into electrical energy. Every time you flip on a light switch, you have Faraday's law to thank.
Wait, so those giant power plants that keep our cities running, they're essentially just elaborate versions of moving a magnet near a wire.
You got it.
Yeah.
The generators and power plants use these rotating coils of wire inside powerful magnetic fields. This creates the electrical energy that powers our homes and businesses.
Mind blown. It's amazing to think that such a simple principle can have such profound consequences. All right, what's next?
The notes now dive into a concept called the energy density of magnetic fields, represented by the equation. Energy density equals B squared over 2ρ. It might look intimidating, but it's actually pretty straightforward.
So much information packed into one little equation. What exactly does energy density mean?
It's a way of expressing how much energy is stored in a given volume of space occupied by a magnetic field. The stronger the magnetic field, the higher the energy density. It's kind of like how a tightly packed suitcase holds more stuff than a loosely packed one.
Okay, I can visualize that. But where does this actually come into play in the real world?
Think about MRI machines again. They use these incredibly strong magnetic fields to create those detailed images. Understanding the energy density of those fields is crucial for both safety and effectiveness. It's not just theoretical, it has real-world consequences.
So those powerful magnets aren't just creating images, they're storing a ton of energy too. Suddenly MRI machines seem even more impressive. All right, let's keep exploring these notes. What's next on the agenda?
Next up in these notes, we're moving from big picture energy to something called a solenoid.
A solenoid. Sounds kind of like a futuristic gadget or something.
It's actually much simpler than it sounds. A solenoid is basically just a coil of wire, often wrapped around a cylindrical core. And when an electric current flows through it, something pretty cool happens. It creates a magnetic field inside the coil.
So we're basically creating a magnet using electricity.
Exactly. And what makes solenoids special is that the magnetic field they produce inside that coil is incredibly uniform, like a perfectly smooth magnetic tunnel.
Why is a uniform magnetic field so important? Does it have any, like, real-world applications?
Oh, tons. Solenoids are used in all sorts of devices, from electromagnets and relays to things you might not expect, like those clicky solenoids that lock and unlock your car doors. Their ability to create a precise and controllable magnetic field is what makes them so versatile.
So they're like the multi-tool of the electromagnetism world.
All right, let's see what else we can uncover. Oh, this next section is interesting. Inductors. What are they and why should we care? Even the notes are asking the big questions.
It seems that this student had a good sense of humor. Inductors are these fascinating components that play a crucial role in electronics. Basically, an inductor is like this tiny energy storage unit for electrical circuits. It stores energy in a magnetic field when current flows through it.
So it's kind of like a mini battery for magnetism. How does it actually store that energy?
Remember how we were talking about how moving charges create magnetic fields? Well, when current flows through the coil of an inductor, it builds up a magnetic field around it. And that magnetic field, that's where the energy is stored. It's like a tiny invisible energy reservoir.
So it's storing potential energy ready to be released when needed.
Precisely. And when that current changes, the magnetic field changes too. And this can induce a voltage across the inductor.
Induce a voltage. Does that mean it can actually push back against the flow of current? Exactly. Inductors resist changes in current, which can be a bit of a headache in some circuit designs, but also incredibly useful for smoothing out current fluctuations or filtering out unwanted frequencies. They're like the stabilizers of the electrical world.
Fascinating. They're like the guardians of smooth electrical flow. Okay, there's a note here that says, self-inductance mind blown. I'm sensing we're about to get into some trippy territory.
Get ready for a bit of a head scratcher. Self-inductance is all about how an inductor's own magnetic field can induce a voltage across itself when the current flowing through it changes. It's like it's fighting against its own actions.
So it's creating its own resistance to change. It's like it's saying, nope, I'm comfy with this current level. I don't want it to change.
A very stubborn component indeed. And the strength of this self-induced resistance is measured by what we call inductance, denoted by the symbol L. The higher the inductance, the stronger the inductor's resistance to any changes in current.
So inductance is like a measure of an inductor's stubbornness or its desire to keep things as they are.
Exactly. It's a key characteristic of inductors that comes into play in all sorts of circuit designs.
Okay, what else is in these notes? Ooh, mutual inductance. Does this have anything to do with the self-inductance we were just talking about?
It's a related concept, but instead of a single inductor fighting against itself, mutual inductance involves two or more inductors influencing each other. When the current in one inductor changes, it can actually induce a voltage in a nearby inductor because of their shared magnetic field.
So it's like they're having a magnetic conversation, whispering secrets through their changing fields.
I love that analogy. You're exactly right. Those changing magnetic fields can have this ripple effect, creating a sort of magnetic communication between nearby inductors.
Okay, that's pretty wild.
Yeah.
But does this magnetic whispering have any, like, practical applications?
Oh, absolutely. One of the most common examples is transformers, those cylindrical devices you see on power poles.
Transformers. The things that sometimes make that buzzing sound. Those play a role in mutual inductance.
They do. A transformer uses two or more coils of wire wrapped around a shared core. Alternating current flowing through one coil creates a changing magnetic field, which then induces a voltage in the other coil. It's like they're passing energy back and forth through their magnetic fields.
It's like a magnetic bridge transferring energy from one coil to another.
Precisely. And the really cool part is that transformers allow us to increase or decrease the voltage of alternating current without losing much power. This is absolutely crucial for transmitting electricity efficiently over long distances.
Wait, so those buzzing transformers on power poles are actually responsible for getting electricity to our homes? I never realized they were so important.
They're the unsung heroes of the power grid. They let power plants generate electricity at a convenient voltage, then step it up to a super high voltage for efficient transmission over long distances, and finally step it back down to a safe voltage before it reaches our homes.
Wow, that's incredibly clever. I had no idea there was so much sophisticated engineering behind something as simple as plugging in my phone charger. Okay, I'm seeing a note here that transformers only work with alternating current. Why is that?
Remember, transformers rely on changing magnetic fields to induce those voltages. Direct current creates a static magnetic field, which wouldn't be able to induce a voltage in the other coil. It's the constantly changing direction of alternating current that makes the magic happen.
So it's all about that dynamic fluctuation. AC keeps things moving and shaking in the world of transformers. Now, let's see what else we can learn from these notes.
Looks like we're moving on to something even more fundamental: electromagnetic waves. These are a form of energy that travel through space at the speed of light.
Electromagnetic waves, like light itself.
Exactly. Light is a type of electromagnetic radiation, but the electromagnetic spectrum is actually much broader than just visible light. It includes radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and even gamma rays.
Wow, so all those different kinds of radiation are basically the same thing. Electromagnetic waves.
Yeah.
That's wild. What makes them different from each other then?
The only difference is their wavelength and frequency. Radio waves have the longest wavelengths and the lowest frequencies, while gamma rays have the shortest wavelengths and the highest frequencies. It's like a giant keyboard of electromagnetic radiation with different keys corresponding to different types of waves.
So what we perceive as different colors of light is just our eyes interpreting different wavelengths within that electromagnetic spectrum. It's like we're only able to see a small portion of this vast cosmic keyboard.
You got it. And just like different notes on a keyboard create different sounds, different electromagnetic waves have different properties and uses.
That's incredible. So how are these electromagnetic waves actually created? What makes them ripple through space?
They're produced when charged particles like electrons accelerate, meaning they change their velocity. Anytime an electron gets a little jittery and changes its speed or direction, it releases energy in the form of electromagnetic radiation.
So anytime those tiny electrons are bouncing around, they're sending out these invisible waves. It's like a constant dance of energy.
Exactly. And these waves can travel through the vacuum of space. Unlike sound waves, which need a medium like air or water to propagate, that's how we receive light and other radiation from distant stars and galaxies.
Wow, so those twinkling stars we see at night, they're actually sending us messages across vast distances in the form of electromagnetic waves.
Okay, the notes mention something called Maxwell's equations. Are those important?
Maxwell's equations are basically the rule book for understanding how electric and magnetic fields behave and how they're connected. These equations actually predicted the existence of electromagnetic waves before they were even experimentally discovered, showing that light itself is an electromagnetic wave.
So Maxwell's equations basically unified electricity, magnetism, and light into a single framework. That's pretty groundbreaking. The notes have some pretty intense-looking equations here with a bunch of symbols I don't recognize. Are those the actual Maxwell's equations? They are. Don't worry too much about the mathematical details. The key takeaway is that these equations describe the fundamental laws governing electromagnetism.
Okay, I'll take your word for it. So Maxwell's equations predicted the existence of electromagnetic waves, which, as we've learned, include everything from radio waves to gamma rays. Are there any practical applications for these different types of waves?
Oh, tons. Radio waves are used for communication, broadcasting, and radar systems. Microwaves, as you might guess, are used in microwave ovens, but also for communication. Infrared radiation is used for heating, sensing, and night vision technology. Ultraviolet radiation is used for sterilization and, unfortunately, in tanning beds. X-rays are essential for medical imaging and security screening, and gamma rays, the most energetic of the bunch, are used in cancer treatment and for studying the cosmos.
Wow, that's an impressive list.
Yeah.
Electromagnetic waves are everywhere. Okay, turning the page, and there's this beautiful diagram that looks like a rainbow. It's labeled the electromagnetic spectrum. What a perfect visual.
That rainbow represents the visible light portion of the electromagnetic spectrum. It's the tiny sliver of wavelengths that our eyes can perceive, with each color corresponding to a different wavelength. But as we've discussed, the spectrum extends far beyond what we can see, encompassing this vast range of wavelengths and frequencies, each with its own unique properties.
So it's like this enormous cosmic symphony of wavelengths, but our eyes can only hear a tiny fraction of the music.
Exactly. It's amazing to think about all the invisible activity happening around us constantly. Our senses only provide us with a limited view of reality.
This is what I love about physics. It helps us peek behind the curtain and see the world in a whole new light. or in this case, a whole new spectrum.
Yeah.
Okay, what other insights can we glean from these notes?
Let's dive into a concept called the Poynting vector, which might sound intimidating, but it's actually a really useful tool for understanding how energy flows in electromagnetic fields.
A vector. That makes me think of those arrows we learned about in math class representing magnitude and direction. What exactly does the Poynting vector tell us about energy flow?
Think of it like a map that shows us the direction and intensity of electromagnetic energy moving through space. It tells us where the energy is going and how strong the flow is.
So if we know the electric and magnetic fields in a particular area, we can use the Poynting vector to figure out how the energy is flowing through that space.
Exactly. It's like tracing the path of energy as it travels through those invisible fields.
This makes me think of things like solar panels, which are designed to capture energy from sunlight. Are they using the Poynting vector in some way?
You could think of it that way. Sunlight, as we've discussed, is an electromagnetic wave carrying energy. The Poynting vector would point from the sun towards the solar panel, showing the direction of energy flow. It's like an invisible energy highway.
That's such a cool way to visualize it. Even though we can't see electromagnetic waves directly, they carry real energy that we can harness and utilize. Okay, let's see what else we can uncover from these notes. Oh, this looks interesting. Polarization. What's the big deal?
Polarization is all about the direction of oscillation of the electric field in an electromagnetic wave. Remember how we talked about those electric fields wiggling back and forth? Well, the direction of that wiggling is what we call polarization.
So if the electric field is vibrating up and down, we call that vertically polarized. And if it's vibrating side to side, it's horizontally polarized.
You got it. And polarization isn't just a theoretical concept, it has real-world applications. For example, polarized sunglasses use filters to block certain polarizations of light, reducing glare and making it easier to see.
So those stylish sunglasses are actually manipulating the behavior of light waves.
Exactly. And polarization is also used in photography, microscopy, and various other optical technologies.
It's a great reminder that even the most seemingly abstract concepts in physics can have practical uses in our daily lives. Okay, the notes mention something called circular polarization. What's that all about? Is that different from the vertical and horizontal polarization we just talked about?
It is. In circular polarization, the electric field vector doesn't just wiggle back and forth in a straight line. It actually rotates in a circle as the wave propagates. It's like the electric field is doing a little dance.
So it's spinning around instead of just vibrating in one plane. That's pretty wild.
It is. And the spinning can be either clockwise or counterclockwise, which gives us right circular polarization and left circular polarization.
I'm getting dizzy just thinking about all that spinning.
Yeah.
But why would the electric field behave like that?
Circular polarization can arise from various factors, including the interaction of light with certain materials, or the combination of two linearly polarized waves with a specific phase difference.
So it's like a more complex dance of electric fields. But does circular polarization actually matter for anything?
Definitely. It has applications in technologies like 3D glasses and satellite communication. Those spinning electric fields are hard at work, bringing us entertainment and connecting us across the globe.
Wow, I'm starting to see those electromagnetic waves in a whole new light. Or rather, a whole new spin. Okay, let's keep going. What's up next?
Looks like we're moving into a topic that can be a real nuisance in the world of electronics. Electromagnetic interference, or EMI.
Electromagnetic interference. What is that exactly?
Basically, it's the disruption of electronic devices due to unwanted electromagnetic radiation. You can think of it like electromagnetic noise polluting the signals that our devices rely on.
So it's like those annoying crackles you sometimes hear on the radio.
Exactly. EMI can come from various sources, including power lines, radio transmitters, lightning, and even other electronic devices themselves. It's like a constant battle to keep those electronic signals clean and clear.
That makes sense. I've definitely experienced EMI firsthand. Sometimes my phone gets all staticky when I'm near certain appliances. Is there any way to deal with this interference?
There are ways to minimize it. Techniques like shielding, grounding, filtering, and using special cables and connectors can help reduce EMI. It's an important consideration in the design and operation of electronic devices, especially as we become increasingly reliant on wireless technologies.
So it's like this ongoing battle against electromagnetic noise pollution. All right, let's see what else we can learn. Oh, this looks familiar. The Doppler effect. Didn't we talk about that with sound waves? Like how an ambulance siren changes pitch as it moves towards or away from us?
You're right. The Doppler effect applies to electromagnetic waves as well, including light.
So if a source of light is moving towards us, the light waves would be compressed, leading to a higher frequency. and if it's moving away, the waves would stretch out, resulting in a lower frequency.
You're exactly right. If a light source is moving towards us, the light appears bluer, and if it's moving away, it appears redder. We call this blue shift and red shift. And astronomers actually use these shifts to measure the velocities of stars and galaxies.
Wait, so by analyzing the color of light from distant stars, we can figure out if they're moving toward us or away from us? It's amazing.
It is. The Doppler effect gives us this powerful tool to understand the movements of celestial objects
Yeah.
and the dynamics of the universe. It's like a cosmic speedometer.
Incredible. These physics notes are taking us from the microscopic world of electric charges to the vast expanse of the universe. Okay, what's next?
Now we're venturing into the truly mind-boggling realm of quantum mechanics. The notes have a section titled Wave-Particle Duality. What is reality? Anyway.
Even the student seems to be questioning the nature of existence at this point.
Okay, I'm ready to have my mind blown. What is wave-particle duality? And why does it make us question everything?
It's a fundamental principle in quantum mechanics that states that light and matter can exhibit properties of both waves and particles.
Hold on. You're telling me that light, which we usually think of as a wave, can also act like a particle, and matter, which we think of as particles, can act like a wave.
Exactly. It's a concept that completely upends our classical understanding of the world. It's like trying to fit square pegs into round holes.
Okay, my brain is officially hurting. How is that even possible?
That's-
It's one of the most counterintuitive aspects of quantum mechanics. But experiments have repeatedly shown that light can behave like a wave in some situations, like when it diffracts through narrow slits, and like a particle in others, like when it knocks electrons loose from a metal surface in the photoelectric effect.
The photoelectric effect? What's that?
It's a classic experiment that really solidified the particle-like nature of light. When light shines on a metal, it can knock electrons loose. But what's weird is that the energy of those electrons depends on the frequency of the light, not its intensity. This is totally unexpected if we're thinking of light purely as a wave.
So brighter light doesn't mean more energetic electrons. That's strange.
It is. This experiment showed that light energy comes in these discrete packets called photons, each with a specific amount of energy determined by its frequency. These photons act like little bundles of energy, knocking electrons loose when they hit the metal.
So instead of a continuous wave washing over the metal, it's like a stream of tiny bullets of light hitting each bullet carrying a specific amount of energy.
Exactly. The higher the frequency of the light, the more energy those photons carry, and the more likely they are to knock those electrons loose.
Wow, it's like light has a dual personality. Sometimes acting like a wave, sometimes acting like a particle.
That's the essence of wave-particle duality, and it's not just limited to light. Matter exhibits this duality as well.
Wait, you're telling me that things like electrons, which we think of as tiny particles, can also act like waves?
Yes, this duality extends to the building blocks of matter. Electrons, protons, neutrons. They can all exhibit wave-like behavior, such as diffraction and interference, which we typically associate with waves.
So those tiny electrons can spread out and interfere with each other like ripples on a pond.
Exactly. And just like with light, the faster a particle is moving, the shorter its wavelength, meaning it behaves more like a particle. Slower particles have longer wavelengths, making their wave-like nature more prominent.
Okay, so the faster an electron is zipping around, the more it acts like a tiny point. And the slower it's moving, the more spread out and wave-like it becomes.
Exactly. And this wave-like behavior is what allows electrons to do some pretty amazing things, like tunnel through barriers that they seemingly shouldn't be able to cross.
Tunneling through barriers. Are we talking about quantum tunneling here?
We are. It's a phenomenon where a particle can pass through a potential barrier, even if it doesn't have enough energy to overcome it classically. Imagine trying to roll a ball up a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. But in the quantum world, there's a chance that the ball could actually appear on the other side of the hill as if it tunneled straight through.
That's mind-boggling. How is that even possible?
It's a consequence of the wave-like nature of matter. The wave function, which describes the probability of finding the particle at a certain location, can extend beyond the boundaries of the barrier. It's like the wave can leak through the barrier, allowing a small probability for the particle to exist on the other side.
So it's not about the particle magically gaining energy. It's more like a probability game, where sometimes the particle wins and pops out on the other side of the barrier.
Exactly. It's a counterintuitive concept, but it's been experimentally verified and plays a crucial role in many technologies, including those transistors that power our computers and smartphones.
Wow, so quantum tunneling is happening inside our devices right now.
It is. Without it, our modern electronics simply wouldn't work.
Incredible. These notes are leading us deeper and deeper into the quantum rabbit hole. What else is in store?
Let's explore another mind-bending concept, Heisenberg's uncertainty principle.
Okay, hit me with it.
This principle states that we can't know both the position and momentum of a particle with perfect precision at the same time. The more accurately we know one, the less accurately we can know the other.
So it's like a trade-off. If we pinpoint the location of a particle, we lose information about its momentum and vice versa.
Precisely. And it's not a limitation of our measurement techniques. It's a fundamental property of the quantum world. The act of measuring one quantity inevitably disturbs the other.
It's almost like those particles are being deliberately evasive, refusing to reveal all their secrets at once.
You could think of it that way. The uncertainty principle highlights the inherent fuzziness of the quantum world.
The notes have an equation here, with a triangle symbol and an H. Is that the mathematical expression of the uncertainty principle?
It is. That triangle symbol represents uncertainty. And H is Planck's constant, a fundamental constant in quantum mechanics. That equation tells us the minimum amount of uncertainty we'll always have when trying to measure those paired properties.
So it's like a fundamental limit on our knowledge of those particles.
Exactly. And it's one of the key principles that distinguishes the quantum world from the classical world.
Okay, I'm starting to see how quantum mechanics really challenges our everyday intuitions about how the world works. It's a whole different ballgame down there. What else do these notes have to offer?
Let's dive into one of the most mind-boggling concepts in quantum mechanics, quantum entanglement. It's a phenomenon where two or more particles become linked in such a way that their properties are correlated even when separated by vast distances.
Linked. What does that mean exactly?
Imagine two coins flipped at the same time. If one lands on heads, you instantly know the other must be tails, right? Quantum entanglement is kind of like that, but on a much weirder level.
Okay, so if we measure the property of one entangled particle, we instantly know the corresponding property of the other particle, no matter how far apart they are.
Exactly. It's as if those particles are communicating faster than the speed of light, which is, of course, impossible according to Einstein's theory of relativity.
So what's the explanation? Are they somehow sending secret signals to each other?
It's not about signaling. It's more like those particles are intrinsically linked, sharing a common fate regardless of distance. Measuring one particle instantly collapses the wave function of both, determining their shared properties.
So it's like they're two halves of a single unified entity, even when physically separated. That's wild.
It is. It challenges our classical notions of space and time, suggesting a deeper interconnectedness in the universe than we ever imagined.
This is definitely one of those concepts that makes you question the very fabric of reality.
Yeah, it is. Einstein himself famously called it spooky action at a distance because it seemed so counterintuitive. But experiments have repeatedly confirmed its existence, forcing us to accept that the universe is far stranger than we thought.
So those entangled particles are out there,
Yeah.
defying our common sense and revealing the hidden weirdness of the quantum world. Okay, what other strangeness can we uncover from these notes?
Let's explore a concept that sounds like something out of a science fiction movie. Quantum superposition.
Quantum superposition.
Wait on me.
This principle states that a quantum system can exist in multiple states simultaneously until it's measured. It's like a coin spinning in the air. It's both heads and tails at the same time until it lands and we observe the outcome.
Wait, so you're saying that an electron, for example, can be in multiple states at the same time?
Exactly. Until we make a measurement and force it to choose a specific state, it exists in this fuzzy probabilistic state, encompassing all possibilities.
So it's not that we just don't know what state it's actually in all those states simultaneously. That's the weirdness of quantum superposition. It defies our classical understanding of the world where things have definite properties. In the quantum realm, things are much more fluid and uncertain until a measurement is made.
The notes mention something called Schrödinger's cat. Is that related to quantum superposition?
It is. Schrödinger's cat is this famous thought experiment that beautifully illustrates the paradoxical nature of superposition. Imagine a cat trapped in a box with a radioactive atom. If the atom decays, it triggers a mechanism that releases poison, killing the cat. But until we open the box and observe the outcome, the cat is in a superposition of being both alive and dead.
Wait, so the cat is both alive and dead at the same time until we look inside the box? That seems impossible.
It does. It's meant to highlight the strangeness of quantum mechanics. and how the act of observation seems to play a role in collapsing those multiple possibilities into a single outcome.
Okay, I'm starting to think that quantum mechanics is just a fancy way of saying anything goes.
It might seem that way, but it's actually governed by these precise mathematical laws that we're still unraveling. It's just that these laws operate on a level that defies our everyday experience and intuition.
These notes are a wild ride through the quantum world. What else is there to discover?
Let's talk about quantum computing, a field that's harnessing these bizarre quantum phenomena to revolutionize computation.
Quantum computing. I've heard it's going to change everything.
It has the potential to. While classical computers use bits, which can be either a 0 or a 1, quantum computers use qubits, which can be in a superposition of both 0 and 1 at the same time. This allows them to explore many possibilities simultaneously, giving them a huge advantage over classical computers for certain types of problems.
So those qubits are like super-powered bits.
Yeah.
Able to tap into the weirdness of quantum mechanics to perform calculations much faster.
You could say that. Quantum computing is still in its early stages, but it holds immense promise for fields like medicine, materials science, and artificial intelligence.
So those qubit-powered machines could be the key to unlocking solutions to some of humanity's biggest challenges.
They very well could. It's an exciting time to be following this field.
These physics notes have been an amazing journey, taking us from the building blocks of matter to the cutting edge of quantum computing. Is there anything else we can learn from them?
Unfortunately, the notes end abruptly. Looks like we've reached the end of this student's exploration, at least for this set of notes.
I feel like my brain has been stretched in all sorts of new directions. I hope our listener is feeling just as energized by this deep dive into the world of physics.
It's been a pleasure to explore these notes with you. Remember, physics is not just about equations and theories. It's about understanding the fundamental principles that govern the universe and our place within it.
Well said. Thanks for joining us on this adventure through the fascinating world of physics. Until next time, keep those minds curious and those imaginations firing.
Yeah, it really does feel like this student's physics journey was just getting started when these notes end.
I know, right? I mean, there's so much more we could explore. But even just with what we've seen in these notes, it's amazing how much ground we've covered from those tiny atoms to the vastness of the cosmos.
Exactly. And we've really seen firsthand how these seemingly simple principles, like moving a magnet near a wire, can have these huge implications for like generating the electricity that powers our entire world.
And then going down to that mind-bending realm of quantum mechanics, where particles act like waves and can tunnel through barriers, and even exist in multiple states at the same time.
Yeah, it's pretty wild.
It really is. It's amazing how physics can connect all these seemingly completely different things
Yeah,
and show us this hidden order and elegance in the universe.
it really is. It's a constant reminder that there's always more to discover, always more to learn.
Well said. And, even though we've reached the end of these particular physics notes,
Yeah,
it kind of feels like our own exploration of physics is just beginning.
I completely agree. There's a whole universe of fascinating concepts and discoveries out there just waiting to be explored.
So to our listener, we encourage you to keep that curiosity alive. Keep asking questions. Keep seeking answers. And keep exploring the wonders of the world around you. Who knows what incredible insights you might uncover.
And remember, physics isn't just for scientists and engineers, it's for everyone. It's a way of understanding the universe and our place within it, a way of appreciating the beauty and complexity of the world around us.
Thanks for joining us on this deep dive into the world of physics. Until next time, keep those minds curious and those imaginations firing.